All right, so first thing I'll do is I'll talk about the assignment. Is there any questions before I do from last week? Okay. So the assignment will be due in 2 weeks. It has you doing a little bit of stride and a little bit of an evaluation framework. So it will be due in 2 weeks, 8 p.m. Okay, so the first thing I'll explain is that if you can't complete the assignment on time, what I do just to manage that is everyone in the class gets what's called a slip day. So a slip day lets you hand it in 2 days late. There's no penalty for doing it. The only rule about it is if you do it on assignment 1, you can't do it on assignment 2. If you don't do it on assignment 1, then you might as well do it on assignment 2. You don't have to email me or anything like that. Okay, you just hand it in late. We'll track who hands it in late on assignment 1 and make sure that assignment 2 comes in on time. Okay, so 2 days would be like Sunday at 8 instead of Friday at 8. Is that clear? Okay, you'll submit it on Moodle itself. So you'll go to Moodle. You'll click on the assignment. The way it looks might look a little different for you than me because we're logged into different kinds of accounts. But somewhere there'll be a place for you to submit it. It's just a PDF. You can just upload it. Okay, so what the assignment does is it talks about concert tickets as the example. So let's say you go and you buy concert tickets. You should have the right to sell them again. Like say in the end you can't go, so you could transfer it to someone else. The problem with reselling tickets is some people will try and buy up all the tickets and then they'll resell it at a higher price, and bands don't like that. And so the point of the assignment is to look at a couple different ways that you could implement a system. Some are physical using paper tickets. Some of them are digital. Some of them, the ticket's tied to your name, so you might have to show an ID when you go in. In other cases, whoever has the ticket can go in. Another thing that happens is you might go and buy tickets on StubHub or wherever. You get the ticket, you show up at the concert, and they're like, oh, the person's already in, we can't let you in. And there's nothing you can do about it, okay? So you also want to think about fraud-proofing it so that if you buy a ticket off someone else, you know that you're getting the ticket. It's not a fake ticket. It's not like there's 10 tickets floating around and there's only one seat for those 10 tickets, okay? So what the assignment does is it actually gives you 3 example systems that it might work, how it might work, so you can read them. The samples are pretty skim on details, okay? So you might want to make assumptions about how they work, or something might not be fully spelled out. That's okay. Okay, so you can just write, wherever it becomes relevant, you might say, I'm not really sure how this system works, there's not enough detail, so I'm going to assume it works like this. Okay, so as long as you state your assumption and then you do your work relative to your assumption, it's fine. Okay, TA will accept all assumptions that are reasonable. Okay, so what you'll do is in the first question, you'll apply stride. And so I'll just sort of go into detail. So what you're going to do is you're going to take the first system. So the first system is called physical ticket system. Then you're going to take the S in stride. Okay? And what I want to know about the S in stride relative to the physical ticket system is I want to know, is spoofing even a concern? Okay, so when it comes to tickets, is spoofing even relevant? It might not be. It might be, it might not be. For all the things in stride, some of them might be relevant, some of them might not be. Okay? If it is a concern with the system, what is the physical ticket system doing to stop spoofing? Okay? So it makes you check a driver's license or whatever. Or the paper is not counterfeit because it has a seal on it or a hologram or something like that. Okay? And then you can also say, is it sufficient what the system does? Does it go far enough? Okay? Or are there still some spoofing attacks that the current system doesn't address? Okay? So those are basically the three things. Is spoofing a concern? Yes or no? If it is concern, what are the actual attacks? Give me some spoofing attacks. And then is the system do a good job of addressing them or not? Okay? Then what you can do is talk about the other two systems. So the e-ticketing system and the online system. These can be in a little less detail because for some of them it might be it's exactly the same as the physical system. Or some of them might be, oh, it's mostly the same, but it's a little different because of this or that. Okay? There's a couple guidelines on how many sentences to use. We're not going to count sentences, but because there's 100 assignments that are coming in and the TA has to read all of them, that's why these limitations are there. Okay, so if you're an extra sentence over or something like that, it doesn't matter. Okay, but we're trying to stop people from writing half a page or a page about one thing. Okay, because you could go into a lot of detail here. Okay, but we just want some quick thoughts in a couple sentences addressing these things. Okay, so once you've done it for S, you've talked about the physical ticketing system, you've talked about the differences of the other two systems for S, then you'll do it again for T, and then you'll do it for R, I, D, E. Okay, and that's question 1. Then in question 2, we want to go toward an evaluation framework. So we're going to compare these three systems. Okay, so what the first task in question 2 is to come up with the sort of the columns that we'll do. Okay. Now we're going to use the UDS framework. Okay. So what I want across question 2 and across question 3 is I want 6 security criteria, 6 usability, and 6 deployability. Okay. If some of them happen to be the same as the passwords that we did in class, that's fine. Okay, you can use them, but this isn't a password system, so I would expect that some of them are going to be different. Okay, so you can use stuff as long as you say where you got it from. You can use whatever you want, but because these papers and things like that aren't specifically about this, they're probably going to be a slightly different criteria. Okay, so 6 security, 6 usability, 6 deployability. And then for each of them, you need to say, what does it mean to get a full dot? What does it mean to get no dot? Okay, and this is a sort of a tip. You're going to do this before you've even talked about what the 3 systems are. Okay, so what it means to get a full dot or no dot has nothing, it doesn't have anything to do with the systems yet. It's just for that criteria. For any ticketing system in the world, what does it mean to get a full dot or not? Okay. Then later, when you evaluate the systems, then you'll consider whether they get the dot or not. If you want to use a half dot, that's fine. So you can define it any way you want. And since in part 1 with Stride, you came up with a bunch of attacks, you can turn those into your security columns. For question 2 if you want, or they can be new. It doesn't matter. Okay. And so, anyways, I just want a couple sentences, like 2 sentences for each thing. What is it? What does it mean to get a full dot? What does it mean not to get a full dot? All right. Then what you'll do is you'll do the evaluation, and just to cut down on your time and the TA's time marking it. I'm not going to get you to do the whole table. What you'll do is you'll just do one row of the table. Okay? So the row I picked is the middle one, the online system. The third one. So that's the one that you'll actually evaluate against your criteria. And you'll just go through and say, okay, I'm giving a full dot because. Okay, so you have to have the reason. Okay? It gets a no dot on this because this. Okay? And you don't even have to draw it. It can just be a bullet list of, here's the columns and what it gets. If you want to draw it, you can draw it, whatever you want to do. Do make sure that it's typed up though, okay? So not a handwritten assignment. Type it up and then create a PDF out of it, and that's what you'll actually submit itself. There's some other papers here that have examples of evaluation frameworks. If you just want to see a handful of them, you can take a look at those. Okay, so that was the main thing I want to say about it. Since you have 2 weeks, you can go through the systems, and next class or anytime between now and next class, you can ask me questions specifically about it. But given what I said, is there any questions about it?
Professor, do we have to mention the references in the ones that you've given if we read them?
If you use them, you can mention them. So the only way you would use it is if you took an exact column out of one of them, then yeah, you can just reference it.
Okay. If not,
And if you don't use any columns from them, then you don't have to reference. Yeah. Okay, it's clear. All right, so take a read through it. If there's questions, you can ask me next week about it as well. Okay, so for today's lecture, what we're going to do is we're going to look at the third high-level methodology. So a high-level methodology is something that applies to anything. This is called an attack tree. And attack trees are nice because even though it's a high-level methodology that you can use for more or less anything, you can still get a lot of detail out of it, okay? Probably more so than Stride. Comparable to a very strong evaluation framework. Okay, so it's a high-level methodology with the potential to reach low-level details. The example we build, we're going to do across 3 lectures. This week, next week, and the week after. And so that's why it's a certain level of detail. It works best when you understand the domain of what you're analyzing. Okay, so that's why I'm taking 3 weeks to do it, is because I'm going to teach you how the thing we're looking at works, plus we're going to think about how to attack it at the same time. Okay, evaluation, they're slightly different in this respect. Evaluation frameworks are used to compare multiple solutions. Stride is generally one solution. And then attack tree is even narrower, where you're considering one property that you want to break in a system, in one system. So one attack on, I'm saying it wrong. One goal that the adversary has in one system. Okay, so if a system is meant to resist, 5 different kinds of attacks from the adversary, you would have 5 attack trees. Okay. If you have 5 different systems, you would have 5 different attack trees. So you're going to have one attack tree. Basically, for every attack on every system, there's a tree for it. Okay, so it's a little more narrow. Okay, so what you're basically going to do is you're going to think about, what does security mean for this system? Okay, and then what would it mean to violate security for this system? So that's sort of the adversary's goal. Then what you're going to do is you're going to try to come up with what are all the ways that the adversary might achieve the goal. Okay, so these are called attack vectors. Some people in security will distinguish between the word attack and threat. An attack in this definition would be something that actually happens or is actually real, and a threat is more hypothetical. Okay, it's something that might work, but no one's actually done it in practice. For this, we'll do both attacks and threats. Okay, so they're both fine. If you want to call it a threat tree instead of an attack tree, it's probably like a better word for it. It's just that everyone in the community says attack tree. Some people do say threat tree, but most people say attack tree. So I'm just using the word attack. But threats are included as well. So if you have something that might work in practice, but maybe it might work, but no one's actually done it in practice, but it's sort of a vector of attack, then that's fine as well. You can include it in the tree. And then you can also combine it with Stride. So Stride can help you think of things to put in your tree, basically. And it's easier to do if you know, like say you're doing it for one security feature of a car, like that has computers in it or something. You have to know about cars and how they work and things like that. Otherwise, you won't be able to do it. Okay, so the actual output of an attack tree is a tree. Okay, it's just English language tree, like with arrows between things. Okay, so it's not like a binary tree or like some sort of data structure like in computer science. It's just like in the previous one we had a chart, right? Now it's going to be a tree, but it's still going to be just like descriptions of things. Okay, so what the adversary wants to do will be the root of the tree. Okay, then every way the adversary might do that starts to branch out. So the adversary might get their goal by doing A, B, or C. So then you have a branch for A, a branch for B, and a branch for C. Then you would go to A and you'd say, okay, well, how do you do A? Right? And then there might be another 3 options. And so it would branch out from there. Eventually you'll reach an actual attack, like a complete thought of how to break the system. And that will be at the leaf of the tree. Okay? And so when you start at the node of the tree, which is the goal, and you walk along a branch, it kind of tells you the story of the attack. Okay? This will be a little clearer in like 2 seconds when we do an actual example. And then the reason it's in a tree instead of just a list of attacks is some attacks are closely related to others. So they're going to be close to each other in the tree. And then there's going to be some attacks that are completely different, take a completely different approach, and so they'll be further away in the tree. Okay? And this is useful for you brainstorming attacks, because once you get one branch in, then you can just kind of go up a node and say, well, is there a variation that I haven't thought about? And then you can go up another node and say, is there a variation? So by putting it in a node and sort of clustering like attacks together, it helps you brainstorm new attacks. Okay, so that's another benefit to using this tree structure. And then a tip, which we'll use in 1 second. We'll do a quick example of one, and then we'll go into the 3 lecture long example of one. The way I like to do it is the root node will be the adversary's goal. Okay. Then I ask myself, what's stopping the adversary from just doing that, right? Usually there's a defense mechanism, right? And then I'll put that as the second node. And then I'll say, well, how would you get around that defense mechanism, right? And then I would go to the third node, so that would be how to get around the defense mechanism. Now, there might be another defense mechanism once you get around the first one, and then you put that in as the next node, and you sort of alternate between this is what I want to do, this is what's stopping me, this is how I beat what's stopping me. Now this other thing is stopping me, this is how I'm going to beat that. And then eventually when you break through all the layers of defense, then you have an attack that's complete, and then you stop in the tree. Okay, so let's do a concrete example. So let's say I park somewhere. I park at Concordia. I'm in the library building, and it's very expensive. It's like $21 to park there for the day or something like that. It might be like $24 now. Okay, I'd rather keep the $24 in my pocket. All right, so I want to leave without paying. Okay, so that's my goal. And so if we're doing an attack tree, I would pencil that in as the root of the tree. So the goal is to leave a parking lot without paying. Okay. Now what I want to do is I want to think of all the ways I can do that. Okay. All right. So using the tip that I just had, I'll start by thinking, well, why can't I just leave? I could just leave, right? Like something's stopping me from actually leaving. So tell me, what is it? Okay, so there's some sort of like arm thing, robotic arm thing that stops me from doing. Okay, so then I can say, okay, well, I want to defeat that arm. Okay, so more specifically, it's that the arm's not opening. Okay, so why can't I just have the arm open without paying?
Because it is controlled by.
Okay, so it's controlled. What's it controlled by?
Either it's a security or
Okay, so now we're branching. Either the security person or there's some sort of machine which is tied to your payment. Okay, so we have a branch. Okay, security person, can they open the door? Yeah, sure. They usually have a manual override. Okay, so then I can think, well, how can I get the security person to open the door if I haven't paid? Okay, so there's some sort of attack, like physical coercion. Anything more clever, less harmful? Okay, you could bribe them, but that's kind of the same thing. You might as well just pay, I think. You might be able to pay less. Say loud. Fake money. Okay, so you could try and, this is more on the payment side. So you have this payment thing. So you could also defeat the payment. If you can make the system think that you paid when you didn't, right, then you can also get through. Okay? So I could do some sort of fraudulent payment. I could try to hack the payment machine, something like that. Back to the human, usually they might have a key or something. If I can get a picture of the key, I'll 3D print a key, and then I'll be able to do it myself. I could tell them a story, right? Social engineering, like I could tell them why, right? Another thing that happened to me accidentally is one time I parked at Concordia. This is actually in the old system. The new system is better. But they used to have like these magnetic cards. So it gave you like a little cardboard card, but there was a mag strip on it. And I just folded it and put it in my pocket, sorry. But once you fold it, it actually wrecks the strip. So then I couldn't pay. I was trying to pay with the machine, because it was folded, it wouldn't accept it. So I just went to the person and said, I folded it, it's not working. And they just opened the door and let me go. Okay? So every day I could just come in, park, fold the ticket, and then go. Now, some of these attacks, and this applies to that whole repudiation category, right? You can do it once, right? But if I did come every day and do it, and it's the same attendant, they're going to catch on fast. Okay, so it's maybe not a repeatable attack, but that's an attack. Okay, so this is the kind of thing that we're thinking of, and this is the kind of thing that could go into a tree. So we could say our root node is to leave the parking garage without paying. And so the thing that stops us is either the ticketing system that wants money, or it's the physical thing of the arm. Okay, so I could try and get around the arm somehow, or I could try and get around the payment mechanism. Okay, and then to get around the arm, there's lots of different attacks. It's not like there's one attack, right? There's a whole tree or a whole subtree of attacks. Okay, so then you just sort of keep kind of like breaking it down. Okay, so first off, we might be able to just physically drive around it. So you can see a picture in the middle. So this is probably one of the worst robotic arms, but you can see there's a driveway. There's lots of grass on both sides of the arm. You can see lots of tire marks. What are people doing? Right? They just drive around it. You could just drive through it and break it. It's fine. Another thing you could do is, what if you drive really close to the car in front of you? Okay. Some cars have like trailers on the back, and the arm doesn't want to come down in the middle of a car, right? So it's going to wait until it's convinced the car has fully passed. Okay. So two cars going bumper to bumper through looks a lot like one car in a trailer going through. Okay. So you could tailgate another car. Another thing you might do is, let's say the power goes out. What happens if the power goes out? No one can leave the garage until the power comes back on? Okay, that could be an option. Okay, that would be the safest, like if you're protecting your money as the parking lot operator, the safest policy for you is to not let anyone out until the power comes back on, right? But what would you do in practice? Well, for a whole bunch of safety reasons and the fact that people have to leave and things like that, you basically have no choice. You're going to open it up and let everyone out for free. Okay. Now, in security, this is a concept that will come up a few times in this course. If the power fails and you keep the arm down, we say it fails closed, meaning when it fails, the security measure stays in place. Okay. The opposite, which is if you open the arm when the power goes out, we say that's a fail open system. Okay, so it fails, and because it's failing, then you turn all the security off, basically. Okay, and the arm opens. All right. So we'll see some other examples of fail open systems later in the course. The other thing is, as mentioned, there's a human. The human has the ability to override, like to open the door for whatever reason, or the arm. So it might be a key-based system, or it might be a button, but the button's in a booth and the booth has a key. So if you can somehow get the key, getting keys is easier than you think. High-resolution photo of a key is enough. Not even high, I shouldn't like oversell high resolution. If I can get a picture of the key from my phone, like say the person's walking around and their keys are like on their belt, right? I just get a picture of it, then I can 3D print a replica key and it will work, okay? Or I could do some sort of social engineering where I tell a story or I, that type of thing, and maybe it works on getting them out. All right, so we have someone driving through the arm. We have people driving around it, and then that's what a 3D printed key would look like. Then on the payment side, you could try to basically, okay, you have the payment, so like the money that you put in, and then the fact that you paid gets registered on the ticket itself, okay? So the ticket says whether I paid or not, and then there's whether I actually paid or not. So those are kind of two separate questions in my mind. Another thing, just let me interject it here, is if I ask everyone in the room to do a attack tree, they're all going to look a little different, okay? So if you're thinking I wouldn't organize the nodes this way, that's fine. That's, this isn't the scientific way of doing it. I didn't use a methodology to make my attack tree look exactly like this, and everyone's going to look exactly the same. Okay, everyone's trees will look different, but the major attack should be in your tree somewhere. Might be organized slightly different. Okay, so anyways, in my mind, I like to split the money and the ticket that registers whether you paid or not. Okay, so you could try to pay fake money. You could try you could also try non-repudiation, where you just say I paid, and they're scanning and says, well, it says you didn't pay. Well, no, I did pay, right? Then there's a standoff. What's going to happen? Well, for $20, they're just going to let you go probably. But again, that's the type of thing that will work once. It's not going to work if you do it every day. And then on the ticket itself, you could try to tamper with the ticket so it has like a barcode thing on it. So like if you could scan it and reverse engineer it, and then you could figure out there's a bit that it's either set or not, depending on whether you paid or not, and then you could set that bit. Then you could maybe get out. You could try to ruin your ticket. That was my accidental approach. Another thing, this is an interesting one, is let's say you go in the parking lot, you drive around, there's no spots, and you want to leave. How much do you pay? Usually nothing. Okay, so usually the thing's configured so the first 10 minutes are free or the first 30 minutes are free, that type of thing, to stop that. Okay, so if I can get a new ticket, right, then I can leave with the new ticket, and because the new ticket thinks that I've only been in the parking lot for 5 minutes, it's going to let me out for free as well. Okay, so what stops you from just walking up to the ticket machine, pressing the button, getting a new ticket, then you go to your car, and then you drive out with the new ticket? Anyone, any ideas? Sorry, the
cameras?
Yeah, so maybe cameras, so that could catch you in the act.
I think it requires the license plate number of the car.
Okay, so it could be some sort of camera-based system that's looking for it. Usually it's a little simpler than that. It's actually on the screen, yeah. Yeah, so a weight sensor. So usually where that machine is, there's actually like a scale, and you need to have a couple tons sitting on that scale in order to think that there's a car there, and then it will give the ticket, okay? So they do it on purpose to stop people from doing this type of thing. Okay, so what's stopping you from getting a new ticket? What's stopping you is the weight sensor, okay? So now the attack turns to the weight. Can you attack a weight sensor? How? Get a bunch of your friends to stand on it, right? So now you get 10 people, they all stand there, you press the button, you get the ticket. You could have your friend pull in with their car, get a ticket, then reverse away. So they don't actually go in the garage, but they give you the ticket, and then you can get out for free. You could also do a sophisticated way is what we call a chain attack. So a chain attack would be, I go in, I park, I'm there for a couple hours, and then I wait for someone else to come in, and basically I switch tickets with them, okay? So then I get out for free because it's a new ticket. Now they're kind of on the hook for the full, not just the time that they're going to spend there, but the time I'm going to spend there again. But if someone's coming in at the same time as them, then they can switch with that person. And so as long as you have a continual number of cars coming in, right, you can always switch with someone new and get a fresh ticket and no one pays. But everyone's holding on to this ticket that's growing and growing and growing in terms of the amount that's owed on it. But this ticket, first off, most parking lots have a cap, right? And at worst, you can say, I lost the ticket. And then they're like, then there's usually a max. They're just like, okay, it's $25 if you lose your ticket. Okay, so you can do this chain attack as long as new people come in. And then if there's no new person that comes in, then you just say, I lost my ticket. And then that one person pays like the maximum, right? But hundreds or thousands of people could have parked for free in the meantime. Okay, so anyways, that's a pretty sophisticated attack. There's a similar attack in voting systems that you can do to attack voting systems called a chain attack. But anyways, okay, so is this every single possible attack to get out of a parking garage for free? The answer is probably not. It's, but it gives you the flavor of an attack tree and what it looks like. Okay, so this is sort of the whole tree that we came up with. Then let me just go back to my tips. Okay. So you can see things like goal, I want to leave without paying. Well, what stops me? Well, what stops me is I have to pay, right? Okay, well, then I'm going to try and get a new ticket. Well, what stops me from getting a new ticket? Well, there's a weight sensor. So how do I defeat the weight sensor? Well, I get lots of friends, okay? So it kind of goes between, this is what I want to do, this is what's stopping me, this is how I beat it. This is what I want to do, this is what's stopping me, this is how I beat it. So that's like a kind of pattern that you can use. You can see that, like, for example, driving through the arm or driving around the arm, those are similar attacks. They're slightly different, but they're similar. Whereas doing this chain attack that we just talked about is like a completely different attack. So it's somewhere else totally different on the tree, okay? And then by organizing it in a tree, you can do things like you can look at the attendees, the fact that the attendant of the parking attendant can override it. So you're like, well, you could print the key, you could social engineer. Then you can say, well, is there another attack that I could do? How else could I, attack the fact that I know that the attendant has the ability to override it? Okay, distract them. I don't know. Maybe like use some sort of physical device so that you can like reach through the window and press the button. Whatever. So because it's kind of organized and you have a smaller goal, it's easier to brainstorm other things that are in the tree. Okay, so that's sort of more or less why an attack tree is a tree, as opposed to just a list of attacks. Okay, and then the final thing is, as you go from node to leaf, so the leaf are all the attacks, the node is the goal, and it tells you a story, right? So I want to leave without paying, but there's this robotic arm, it's stopping me, so I'm going to trigger a power outage so the arm doesn't work, and then they're just going to leave the arm open. Okay, so that kind of tells the story of the attack from start to finish. Okay, is this clear? Okay, so this is the kind of thing, like evaluation frameworks, that looks super obvious, right? You look at this tree and you think, yeah, that's easy to do, okay? But again, the devil's in the details, right? It's hard to actually, when you're looking at a blank tree and you have nothing, coming up with these attacks, that's the hard bit, okay? So once you come up with the attacks, putting them into a tree is easy. That's trivial, right? But it's looking for the attacks and thinking of what are the related attacks. And then when you think you have a pretty good tree, asking the hard questions of like, did I miss anything, right? Is there other types of attacks? So that's sort of more or less what makes it difficult. Okay, so what we're going to do is we're going to do a bigger example now for a couple lectures. And what we're going to do is we're going to study a protocol. It's a networking protocol, something that everyone's used in the room, whether you realize you use it or not. It's called HTTPS. So I'll go a little bit through what it is, the goals of HTTPS are. Then I'll tell you what attack tree we're going to build to break this protocol, and then we'll just jump into trying to come up with things. Okay. So HTTPS stands for HTTP Secure. Basically what it does is it tries to give you a secure tunnel between your computer and a website that you're visiting. Okay? Secure tunnel means I could send a credit card number over it. And even if there's people in the middle, like the Wi-Fi router, like the ISP, like the backbone servers on the internet, even though they're in the middle and they can see the traffic, because I have a tunnel and I'm putting it in the tunnel, they're not able to read it. Okay, so they don't know what my password is. They don't know what my credit card number is. Okay, HTTPS is basically a combination of two technologies. So HTTP is just the network protocol for like asking for a website and getting a website back. Okay, that's more or less the level of understanding you have to have. We're not going to go into detail of it. And then in order to make this tunnel, we're going to use something called cryptography. You'll learn about crypto in 6110 if you haven't taken it yet. If you haven't, it doesn't matter. You don't need to understand it to understand this. And so the cryptography comes from a library or like a suite of things. It's technically a standard, and then it gets implemented in various libraries. It was originally called SSL. Now it's called TLS. It had a name change halfway through. So you can think of HTTPS also as HTTP over SSL/TLS. Okay, so SSL, TLS, HTTPS. Sometimes I'll use the terms kind of interchangeably, but technically SSL, TLS means just the crypto. You can apply it to things that aren't HTTP. Okay, you can use it for other stuff. And similarly, HTTP, you don't have to use it. We all know that you don't have to use it with SSL. You can just send stuff in the plane. That would be normal HTTP, or you can use HTTPS. Okay, so on the cryptography side, SSL, the very first version, 1.0 was just an internal discussion within Netscape. And then they finalized it. They worked a bit with the government. And then they came out with SSL 2.0. So the first public release of it was at 2.0. And that came in the 90s, okay, 1995. Then we have an SSL version 3. Then they switched the name to TLS. SSL stands for Secure Session Layer. TLS stands for Transport Layer Security. If any of you have taken like networking and you know like the OSI model, you know that sessions are one layer and transport's another layer. And so SSL sounds like a session layer thing because it's called Secure Session Layer, right? But transport layer security sounds like it's at the transport layer. And so that was the motivation behind the name change, is to put it where it should be in the OSI stack. Anyways, so then there's 1.0, 1.1, 1.2, 1.3. 1.3 is our current version. Okay, so it was released in 2018 as a standard. Most browsers implemented it more or less right away. Or they had already implemented it before when it was under discussion. And so TLS 1.3 is what your browser, if you have all your software updates and everything like that, it's what it would prefer to do. And most websites will support it. TLS 1.4 is under discussion. So every time there's a new release, they're already working on the next one. 1.4 will have more kind of solutions to the threat of quantum computing, which could break a lot of TLS 1.3 and break all of TLS 1.2 and earlier, depending on which types of primitives you choose. Okay, so what does it look like? Let's say you go to a website and you have that secure tunnel in place, and you go to a different website and you don't have that secure tunnel in the place, right? You're only supposed to send your credit card number or your password if the tunnel's in place. So the user has to know whether the tunnel's there or not. Okay? So how does a browser tell you whether the tunnel is there or not? And the answer is there's two ways. Okay? One way is it will display a lock beside it. Okay? And the other way is if you were to click on the URL and go into detail, you would see that it's https:// as opposed to http://. Okay? This is also a way that you can request the lock. So let's say there's a website and it has both, and you want the lock version, right? Then you can explicitly type in https, and then your browser will at least ask it. The website might say no. Then your browser will say there's an error, it doesn't support HTTPS, or it will send you to the HTTPS website. Okay? These things more or less mean the same thing, but HTTPS here actually just means that you asked for the website over HTTPS. The lock is kind of like a later stage where you asked for it, you got it back, and we checked it all out, and we like the tunnel that we see. Now we're going to show you the lock. Okay? So it's not possible to have the lock if you don't have HTTPS. Okay? But it is possible that you asked for something over HTTPS, it gave you something back, but your browser doesn't like what it sees. Like there's some sort of tunnel in place, but the browser isn't happy with the tunnel, then it might not show you the lock. Okay? So it is possible in some weird corner cases, but usually it's going to show you something like a lock with an X through it, or it's going to give you an error message that you have to click through or things like that. It's usually just, it won't just sort of happen without you knowing that there's something wrong. Okay? And we'll see some examples of what triggers those conditions and how the browser presents it to users later when we see specific things. Okay? So a lock basically means the tunnel's in place. HTTPS means I asked for the tunnel, and hopefully it's in place or not. All right, so let's use an example. So let's say that for a long time, Wikipedia was a good website that always had HTTPS support, but also had things over HTTP. Okay, now it's HTTPS only. Most of the web changed, and we'll go through the reasons why eventually. But let's say you have a website like that where there are two versions. You want to go to the HTTPS version, or you're just curious, like why is it that some users end up on one version or some end up on another? Okay, so what are all the ways that you could end up on the HTTPS version as opposed to the HTTP version? Okay, so they are as follows. The first is because you explicitly asked for it. How do you ask for it? By typing it in. Okay, most people would just type in wikipedia.org, press enter. Okay, now the browser's filling in the http:// for you, or the https:// for you. Okay, so if you explicitly want HTTPS, you have to type the full URL in, including the https:// and then www.wikipedia.n.org or whatever it is. I forget. Okay, now most people aren't typing URLs in. Okay, sometimes you are, but usually you go to websites because you click on links. Okay, so let's say I go to Wikipedia because I was reading some other article and it linked to Wikipedia. Do I end up on the HTTPS version of Wikipedia, or do I end up on the HTTP version of Wikipedia? Okay, and why?
Depends on the website you're coming from.
Okay, and so the website that sends me there, that puts the link in, they actually choose, right? So when they put the link in, they will put in either HTTP or they'll put in HTTPS, all right? And so they're choosing whether to direct me to it or not. So I'm not choosing it myself. Wikipedia is not choosing it themselves. It's actually the website that's referring you to it. Another thing is that your browser just sometimes knows that, like, Google is always over HTTPS. Well, how does it know it? Well, maybe you're using Chrome and Chrome's from Google. So Google knows its own stuff, right? Or it's some other famous website. Does it know about Concordia.ca? Maybe not. It's not really famous enough. Does it know about pulpspy.com, my website? Certainly not, okay? And so is there some way I could tell browsers, hey, I always use HTTPS, okay? And so it turns out there is a standard. It's called pinning. And so what I can do is I can set some stuff in my website, and then if somebody goes to my website, like how every browser comes to know about that is sort of complicated. But the simplest case would be, let's say that Google is just searching the web with their bots, right? Because they're a search engine, they'll pick up the fact that I have this set that I only serve over HTTPS. Then Google will know about it. Then when Chrome comes out, they'll say, hey, what are all the websites that we know about that are only over HTTPS because our bots picked them up when they were searching the web, building our search engine. And then they'll take that, and it's called a preload, and they'll put it in Chrome, and then they'll push it to all Chrome users. Okay? So my website could end up as a preload in Chrome because the bots picked up the fact that I set this like flag on my website. Okay? The other way it works is if you come and just visit my website, at first you actually don't know whether I serve HTTPS or not. Okay? But once you visit me, I'll tell you. Okay? Now the only problem is I'm going to tell you over HTTP, and because I'm telling you not over a secure tunnel, then the adversary could change that. Okay? But if you can visit me once and actually have a true interaction with me, then for every future interaction that we have, you'll know that I only serve HTTPS. Okay? So this threat model we sometimes call trust on first use, or TOFU. So there's a lot of things that work this way. Like, for example, SSH. So if I log into a computer, the computer will say, here's the certificate that the computer's claiming is their own. Now I can go call the person who runs that server and say, what's your certificate value? Okay? Or I can just say, yeah, it's probably right. And then my computer will remember it forever. Well, not forever, but until it expires. Okay? Then if someone changes the certificate in the middle later, I'll get a warning about it. It will say, well, the server certificate changed. You know, maybe you're being attacked. So anyway, so there's a bunch of web that works on this trust on first use. It's better to just get the certificate and know that it's right. If I could decide that, that's the best world. Trust on first use is sort of a middle world where it's better than nothing. But we'll revisit that later. Then the final thing you can do is maybe Wikipedia wants you to use HTTPS, but it still supports HTTP. And all it does is it forwards you to HTTPS if you try to visit it over HTTP. So that's another way you can end up on HTTPS is you actually try to go on HTTP and then the website just bumps you up to HTTPS. The other problem the problem's kind of the same with this, which is that the procedure for bumping you from HTTP to HTTPS is happening over HTTP. Okay? So in other words, if you go to a website without a secure tunnel, it's going to say, come back and visit me over a secure tunnel, but it's sending that not over a secure tunnel because you don't have it yet. Okay? So the adversary can tamper with that and they can basically stop you from redirecting. Okay? So if I want to stop you from going to the HTTPS version, a redirect isn't good enough from the website's perspective because I'll just stop the redirect, which I can do because it's all happening before the tunnel's in place. Okay? And so one tricky bit about SSL in general is you don't have a secure tunnel until the end. Like you have to send some messages back and forth to set up the tunnel. But by default, if you don't have the tunnel till those messages are sent, then you're sending those messages back and forth without a tunnel. And the adversary can do whatever they want. Okay? So you have to figure out how to solve that from a cryptographic perspective. There are answers to that question that will not be covered in this course, but you can take 6110 and you can learn what those answers are. Or ask me questions about it. Okay. Next thing is, what does HTTPS actually do? So we use this analogy of a secure tunnel. But what does that mean? Okay. So like I said, let's say I'm on my laptop. I'm going to Concordia's website. I have a secure tunnel in place. It's meant to protect me from an adversary that's in the middle. Okay. Now, back when we use sexist language, everyone just said man in the middle because everyone were men. Okay, so I'm going to abbreviate to MITM, man in the middle. But of course, it doesn't have to be a man. Okay, probably it's not even a human. It's probably some sort of machine or something like that. You can call it machine in the middle or malware in the middle if you want to backronym that term. But anyways, okay, so I want to protect from the man in the middle. Okay, what does that mean specifically? What protection am I looking for? That's an open question. So tell me, what protection do I want? What can they do? Okay, so spoofing, tampering, but like say it more specifically, not just like a stride category, but like what does spoofing mean or what does tampering mean? Okay, so let's start with read. Okay, so I send a credit card number over, right? They can read it off of the tunnel. Okay, so that's the main, or that's a property of the secure tunnel. Okay, so I shouldn't be able to see what's going on in the tunnel. Is there anything else? Okay, so let's start. So tampering, forging, editing data. So the second thing is they shouldn't be able to change the messages that go by. Okay, and we can't stop them from changing it. Okay, they can change it, right? They're in the middle, they can change it, or they can drop it, or they can do whatever they want. That's too strong of a property, we can't achieve that. But what we can do, which is the next best thing, is we can make it so that if they change it, both parties know that it was changed. Okay, they can detect that it was changed. Then you can ask for it again, and if they want, they can always do a denial of service attack. They can always just not forward traffic, and so they can always stop you from talking or just mess up things on purpose. Okay, so that's always going to be possible. We don't have a solution to that problem with this protocol. Okay, but yeah, we're going to stop them from tampering it, and technically we're making it detectable. Okay, so any tampering is detectable that's done in the channel. Any other ideas?
Redirection?
Okay, so what is that? Can you give an example?
Say you want to access
Yeah.
Facebook.com.
Yeah.
If you don't type it in the URL, the man in the middle can redirect you to Facebook.com.
Okay. Right. Okay. So let me phrase what you're saying is almost exactly right, but subtly different. Tunnels have a beginning and an end, right? So where does the tunnel end? So I want a tunnel to concordia.ca. I don't want it to concordia.com or some other thing. How it comes about that I go somewhere else, just set aside, okay? But I want the tunnel to end where it ends, okay? What if the tunnel ends before it even leaves my computer? Okay? In this case, I still am sitting there putting messages in the tunnel, so I think everything's okay, right? It goes in the tunnel, that's all I can see. I don't see where it ends. It might end at the Wi-Fi router. It might end in the middle of the internet, like the backbone of the internet. It might end at the adversary's fake website for something else, okay? So tunnels don't work if you don't know where they end. Okay, so that's the third property we want, which is server authentication. Okay. All right, so message confidentiality. You can't read data even if you're in the middle. You're not able to read it. That's what the tunnel protects against. Integrity. Any modification that's made by the adversary is detectable by both parties, and they'll reject it. And then the third thing is server authentication. The user knows where the tunnel ends. So if I think I have a tunnel to Concordia, it actually goes to Concordia. Okay. All right, so these are the three properties that we want, and they're the things that HTTPS should provide. So if it works correctly, right, then you have all three of those properties. So I should say that a lot of people will only get the first one. They just think about the first, but they don't think about the other two. But the other two are equally important, okay, as you'll see. So integrity is important because, say you're downloading something and I just stick malware in the middle of it, you don't want that, right? And server authentication is important because if I can end the tunnel somewhere else, then everyone thinks it's great because I have a secure tunnel, but it's actually, you're securely giving all your data to the adversary, right? Which is exactly what you don't want. Okay, so this is just illustrating the idea that in this picture, if the adversary is in the middle and there's a tunnel that ends at the adversary, if you don't have server authentication, then you don't know it. All you see is that you're putting data into a tunnel, right? You don't know where it ends, right? And then the adversary can also create a tunnel between them and Concordia, and they can just relay information back and forth. And then first off, they can read everything now, right? And if they want to make a change, they can make a change, right? So they get something, you send something, they change it and then pass it on, or vice versa. Concordia sends you something, they change it and pass it down. And everyone's happy in this picture. Concordia thinks it's talking to a user over a secure tunnel. The user thinks they're talking to Concordia over a secure tunnel, right? But the adversary's in the middle. Okay, so what we're going to do is we're going to build an attack tree. And we could kind of, we could try and come up with different attacks that violate these different properties, okay? But remember, I said an attack tree is one attack on one system, okay? So the system that we're doing is HTTPS, so we're just going to do one attack on it. It's not the only attack, but it's one attack. So we're going to attack the confidentiality property, okay? So we're going to build an attack tree, which is, my goal as the adversary is to observe the traffic, even though it's sent over HTTPS. And we're going to assume that I'm already in the middle, okay? How I get myself in the middle, I don't know. That's not in the attack tree, okay? There are ways of doing it, and we can go through all the ways. You could do an attack tree on just how do you get yourself in the middle, okay? But we're just going to assume that I'm already in the middle. So what can I do from that middle position, okay? Now, if HTTPS works correctly, the attack tree is empty. Okay, because this is what it's meant to protect. This is exactly what it's meant to protect, okay? But if there's ways of breaking it, then we'll have some stuff to put in our tree. And we can also explore threats as opposed to attacks, meaning maybe this would work or maybe this wouldn't work, okay? Turns out that there's lots of attacks, and so we'll have no problem filling a couple weeks of lectures with just actual attacks that did happen, at least at one time. A lot of them are you know, attack happens and then it's fixed and things like that. Okay, so the way we're going to do it is we're going to, just to get us started, the first level of nodes is we're going to try 3 different strategies to achieve our goal. Okay, so our goal is to observe the traffic. So using the tunnel analogy, the first thing we're going to do is we're going to just think about, let's say the adversary actually does nothing. Okay, they don't actually try to break it. They are seeing the data go back and forth in the tunnel, kind of, okay? So they are seeing something, right? So we can first off ask ourselves, well, can you learn anything, even though it's in the tunnel? The tunnel's an analogy. Basically, it's encrypted, okay? So you're seeing a bunch of like garbage, like noise go back and forth, okay? But you are seeing something, okay? Can that tell you something? Can you learn at least something about what's being said, even if it's all encrypted and it's all noise, okay? So that will be the first strategy. What can we learn if we're just outside of the tunnel listening into the tunnel? The second thing we'll do is we'll ask ourselves, how do we break into the tunnel, okay? And then the third strategy will be, how do we get this picture where we trick the user's browser into thinking we're concordia.ca? Okay, that we'll authenticate to the user and tell the user we're concordia.ca. The user will be so confused that they'll actually accept it. The user thinks they're talking to concordia.ca, but they're really talking to us. Okay, then we can read all of the data. Okay, so those will be our 3 kind of high-level strategies. So what can we see from outside the tunnel? How do we actually break into the tunnel? And then how do we get the tunnel pointed at us instead of at the adversary? Okay, so we'll start with the first one. Okay, so a sort of fancier, more nuanced way of putting it is recover partial data from external observation. So external observation means we're outside of the tunnel. We're looking at what's going back and forth, okay? And recover partial data means I'm going to accept attacks where maybe you can't recover everything that's being sent back and forth, but you can get some information about what's being sent. Okay, that in some scenarios that's good enough. In some scenarios you need to know exactly what's being said, but in other cases it's good enough to just know a little bit about it. Okay, So for this part of the tree, we're going to assume that there's no flaw in HTTPS itself. Okay, so it's working exactly as correctly. It's implemented exactly correctly. There's no crypto attacks, nothing like that. Everything is working exactly how it should. And we're still going to ask the question, do we really learn nothing? Does it really offer complete, comprehensive privacy as a protocol? Or are there weaknesses in the protocol itself? Okay, things that the protocol doesn't, either tries not to do or it can't do for whatever reason. Okay, so let's say that we have a user, Alice. She wants to go to concordia.ca. All right, so this is just sort of background on how it works. So what's the first thing? How do I go to concordia.ca? I want to load the website that's at concordia.ca. Okay, so I go in my browser, I open it up, I type in https://concordia.ca, I press enter. Now what happens? Okay, so what's DNS? Why?
DNS just check the IP address of the main.
Okay, why do I need what's an IP address?
Server address.
Okay, but why do I need one?
Location.
Why can't I go to concordia.ca? Yeah, it fills data, but
Because the
okay, not for authentication. Good guess, but
Concordia.ca is user friendly and we have to translate it to the server address. Otherwise,
yeah. So complete that thought. Otherwise,
Otherwise, it will go somewhere else.
okay. So not necessarily. It actually just doesn't know where to send it. Okay. So the basic idea is that my internet wire at a physical level actually is connected. There's some path through all the wires and machines that it goes through to every other server in the world, right? And I just don't know where to send the packet, right? It's going to reach one of these routers and it has multiple paths it can send it along and it doesn't know, okay? So what we do on the web is we give every server a unique number and it's sort of hierarchical. So like every number that starts with this goes this way and every number that's less than it goes this way. Right? And then you get a little further down and you're like, okay, every number that's bigger than this goes this way, everything that's less than is this way, and then eventually you'll go to the right machine. Okay? So it's just like a phone number, like you have an area code that gets you into Montreal, right? And then you have the actual number which gets to your actual phone, or it gets to Bell as opposed to Videotron, and then it gets to your actual phone number. Okay? So that's how the web works. So you can't route anything without some sort of address that's like routable. IP addresses are what they use, but we don't remember IP addresses. What's Concordia's IP address?
I don't know.
Okay. What if you actually typed it in? Let's say you did know it and you put https://87.4.87.126 and you press enter. It would actually go to Concordia. Like there's no problem with it. It will go there. You'll get the website. It will look kind of weird in your bar, but otherwise you won't know anything's wrong. The certificate might fail for other reasons, but anyways, okay. So how do we get? So let's just go through this again. So we want this IP address thing. Okay. I only remember Concordia.ca, so I want the IP address for Concordia.ca. Does my computer know it? Why doesn't it know it?
It's not a DNS server.
Okay, why can't it be?
So like must be changing over the times if they are migrating from one to another server. So basically DNS record all the new latest IP where server is hosted.
Okay. So let's go through this in slow motion. Okay, my computer doesn't know it, okay, because it's changing all the time. I can't keep up. So who do I ask? I ask DNS, which is its own thing. Like there's a whole bunch of computers and stuff, but we'll just draw a big black box around and call it DNS. Okay? All right. I don't know it because it's changing all the time. But DNS knows it, but it's changing all the time. So what's special about DNS? How does DNS know if it's changing all the time, but I don't?
Because they maintain a table like group DNS.
Okay, why can't I maintain a table?
Storage.
You can maintain the local.
If we make private DNS, then also we can.
Okay. So the answer is I could actually do it if I wanted to. The reason I don't want to do it is because it's like I'd have to know every IP address of every server on the web, and I just don't care about it, right? My phone doesn't want all that bandwidth. My computer doesn't want it. So I'd rather just have a server that does it for me.
Even
Okay.
if I have communication with the Concordia.ca earlier, I don't need to ask a DNS every time.
Okay, that's true. That's true too. So the other thing is your computer will cache it. Okay, so once you resolve it once, especially because sometimes you go back and forth, like you get an image and, you know, in a split second, you might ping the server 20 times or 100 times. You don't want to do a DNS every time. Okay, so once you get it, you'll remember it for a while. The DNS will tell you how long to remember. Okay, and that information is put by Concordia themselves. So if Concordia changes their IP address, they tell their DNS resolver or their registrar what the new information is. The registrar somehow, it's kind of complicated, but it circulates it amongst all the DNS things. Sometimes it takes time. So if you change it, it won't necessarily reach every other DNS server. But usually within 3 days maximum, you'll have fully propagated DNS records. Now all of DNS knows what it is. Then it will give you your IP address.
Most of the time the IPs don't change. Because of the load balancing, you have different IPs. But those IPs will be the same, maximum time.
Yeah. So sometimes there's different architectures for how you want to handle a lot of bandwidth. So you might have one kind of gateway that has a constant IP, but once you hit the gateway, then you're redirected to another IP address. Or you might use something like Cloudflare, which is a CDN, content distribution network, and it has its own architecture, and it's actually very relevant for this HTTPS stuff, but I'm not going to touch it. But the way you do HTTPS with Cloudflare is different, and it kind of complicated, and there's attacks there that aren't normally there. All right, so I go to DNS, and it says, oh, concordia.ca, fine, that's 132.205.244.70. So now I know where it is, or I can route packets to it. So I'll start doing that. All right, now let's say the adversary is between me and DNS. Let's say they want to redirect me to their fake Concordia website. Okay, their fake Concordia website has an IP address. What if they just lie and tell me a different IP address? Is that possible? Okay, why is that possible?
DNS record can be changed by anyone. Like it's you can do DNS poisoning whenever you request someone DNS server, it returns some address. You can alter if you are in middle of the communication.
Okay. So there's I guess subtly two different attacks. So poisoning would be I actually change what this server thinks is Concordia's IP address. So the server now thinks it's my IP address instead. And there are attacks there, but I would be very cautious to say you can just do it. It's actually really hard to do, and there's a lot of defenses against it, and it's more or less impossible. If you could actually do it, then phishing and things like that would be horrible today, okay? So in general, we're gonna assume in this class that it's hard to do those kinds of attacks, but we will note them. So somewhere in our tree, poisoning DNS will show up in our tree. But the easier attack is DNS actually has the right address. It's just when it tells me what the address is, the adversary jumps in the middle and says, oh, it just changes it. Okay? All right. Could it change it if I have a secure tunnel between me and DNS?
No.
It can't, right? That's one of the properties of the secure tunnel. Okay? All right. So then the million-dollar question, do I have a secure tunnel to DNS?
Yeah.
So some people say yes. Some people say no. Who thinks yes?
You said to develop a secure tunnel, we have to do some kind of communication.
Yeah, that's right.
But if I'm doing the first time communication, I won't have the secure tunnel.
Okay, all right. So that's going to be a problem when I go to Concordia. You can ask that question. You should be asking that question in your mind. If I go to Concordia for the very first time, what's going to happen? Okay, let's assume we can solve that problem. I have a solution to that problem. Okay, so you can go somewhere for the first time and know you're talking to who you're talking to. Let's assume that that's true. In that case, could I have a secure tunnel? Okay, let me put it this way. Could I have a secure tunnel to DNS? Yes. So the answer to that is yes. Okay, I can have it. I can do HTTPS to get my DNS requests. Okay, that's fine. Then the next question is, do I in practice? Okay, I don't expect you to know the answer. I'm just soliciting guesses, right? All right. So the answer is it's in between. So generally the answer is no. Okay. We don't tend to do it in practice. Why don't we do it in practice? Well, it's slow. Okay. First off, it does require back and forth a bit. So instead of just saying, give me the IP address and I get one message back, it's like, hey, how are you? Hi, how are you? Here's my certificate, blah, 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 right? Then there's other protocols that will sign the DNS records. Okay, so it'll come with a digital signature. But the problem is the digital signatures are really big. Plus you have to get stuff to check that the digital signatures are right, called certificates, we'll talk about later. And anyways, the whole infrastructure of that is heavy on the DNS server. So that's called DNSSEC. We talked about it when we talked about amplification attacks, because asking for an IP address and getting back it plus a signature plus certificates and all that stuff is a much bigger packet than what you asked for. You can use it to redirect and attack websites to do denial of service. Okay, so in general, DNS does not in practice DNS is not secure. Okay, so all your DNS requests basically leak. Period. Okay. So let's say that the user is going to a website like Concordia.ca. I'm an adversary in the middle, right? That was our goal. Do I know that they're at least going to Concordia.ca? How do I know? Okay, because I'm in the middle and they had to get the IP address and they had to ask DNS for it, right? And I saw that. Okay. So even though there's HTTPS, I already know what website they're going to. Okay. Now it turns out that this isn't a big deal anyways, because in order for my secure tunnel packets to get there, I have to put the IP address of where I'm going anyways. Okay. So even if they didn't eavesdrop on my DNS, they could eavesdrop on any packets and that IP address is going to be everywhere. And I can do a reverse DNS lookup. Okay. But that's the first thing to remember, is the domain name itself is not protected. So HTTPS doesn't stop you from knowing, from anyone in the middle knowing what domain you're visiting. And sometimes domain names matter. Okay. So if you are in a corporate environment and you see people going to, I don't know, WikiLeaks, right? Or some pornography website or whatever, a lot of these things are in the domain name, right? So you can immediately know. It doesn't really matter what they're doing on the website. You might not be able to see that, but it can be enough to just know that you're going to a specific domain. Okay? So you don't have privacy in terms of the domains that you visit with HTTPS. It's not something it strives to do, but it just bears remembering. Okay? All right. It's 7 o'clock. Let's take a 10-minute break, and then we'll go through the rest of this. Okay, if everyone can quiet down. Thank you. Okay, so let's go back to our journey of trying to visit Concordia.ca. Alice asked DNS. She has the IP address now, so she's able to go. So DNS queries are not encrypted generally. The adversary, I mentioned DNSSEC. DNSSEC actually only stops you from changing it. It doesn't stop you from reading, so it provides integrity only. There is a protocol called DNS over HTTPS that gives you both. So it gives you privacy and it gives you integrity. The only problem with it is it's a three-way handshake before you get the data. With DNS, it's UDP, so you ask for it and get it back, and then that's it. Okay, now we could ask the same question of, let's say the adversary's in the middle, rather than between me and DNS, the adversary's in the middle. Do they know what domain I'm visiting? So the answer is yeah, they can see the IP address. The IP address has to be on the outside of the tunnel. Otherwise, the tunnel doesn't know where to go. Okay, or all the data that's sent through it doesn't know where to go. A better analogy might be an envelope. So think of it as an envelope. The stuff you're putting in the envelope stays secret until it gets to the end, then the person opens the envelope. But the mail service has to know where to deliver the envelope. Okay, so IP address is that delivery information. And as I mentioned, just knowing the domain itself can leak information about like things that the adversary might care about. Okay, now let's say that, here's another example. So let's say I go to Wikipedia. I actually don't, I'm a Toronto FC fan, but there's a soccer team here in Montreal called CF Montreal. I want to read about them, so I go to Wikipedia and I want to access all of that information, okay? All right, so this is how a modern website like this will work. So first I'll do the same thing. I'll just go to DNS, I'll get the IP address, then I'll go to Wikipedia and I'll say, what I want is this website here. So if I open that URL up here, you would be able to see that the thing is called index.html or whatever it's called, okay? So I'm asking for that website. And so we're going to assume that HTTPS has already kicked in. So we have a secure channel here, okay? And generally, like at the level that you need to understand this course, you don't need to know much about how like HTTP itself works, but basically you ask for stuff and you get stuff back, okay? The things you ask for are called requests. Sometimes we'll say REQ for requests. There's different kinds of requests. There's a GET request and a PUT request, but we'll use GET and requests basically interchangeably, okay? So I just say, give me this thing, and then I get back this response, okay? Now, when I look at index.html, I see the website that I want to see, okay? Now, let's look at this website. Is everything that I'm seeing right here inside index.html? Okay, look at what is on the screen. Can you point out anything that's not in index.html that's on the screen in this picture? Okay, let's talk about the pictures. Is the picture actually embedded in the HTML file? No. Okay, it's not. Okay, so what is in the, like somehow the picture got there, so what happened?
Put it in some storage, then fetching from there.
Okay, so what I put in the HTML file is a command to go get the image from somewhere. So I'll say, I want an image. Here's a box for it, how big, how many pixels I want it. I want you to go to this address, grab the image and download it, and then stick it in and then show it to the user, okay? So that's called a resource. So when you download a website, you don't get everything at once, okay? You get kind of a skeleton template of the page, and it has a bunch of pointers to other stuff that you have to go and get, okay? Now, I got the index.html page from Wikipedia. Where do I get the image from? Does it also come from Wikipedia? Not necessarily. Okay, it can literally be any URL. It could be a completely different domain. Okay, here's a question I won't answer now. Think about it. I make a secure tunnel to Wikipedia. I download Wikipedia's page. Comes down over the secure tunnel. It tells me go get an image. You need the logo of Montreal Impact. I don't have a secure tunnel to get the logo. Okay, so I get the logo, but it didn't come over a secure tunnel. I put it in the website. Do I show the lock to the user or not? Some of the stuff came down over a secure tunnel, some of it didn't. Think about that. Just keep it in the back of your head. We'll answer the question soon, okay? Okay, so basically I go to index.html. Index.html says, hey, there's this like logo.png file that you need to get. It's at upload.wikipedia.org. Any subdomain is technically a completely different computer as far as the internet's concerned. It could have a completely different IP address, okay? So even though both of these are wikipedia.org at the end, the internet doesn't care. It just thinks that this is a different computer. And it may indeed be a different one, or it might be the same. In DNS, you can give a whole bunch of domains and give one IP address for all of them. But anyways, so I'll go get the logo, then I'll get the logo back, and then it will get loaded in the website. Okay. Now we're in the middle. Okay, so we're seeing this interaction. Okay, so what do I know from being in the middle? I know that the user went to wikipedia.org. I don't know what they requested. Okay, so let me put it as a question. Do I know what they asked for? No. Do I know it was a GET request as opposed to a PUT request as opposed to something else?
Yes.
Okay, so yes, no, maybe. Is it in the envelope or out the envelope? So the general rule is, do you need to know it? Okay, so does someone routing that packet need to know what kind of request it is? So the answer is actually no, it doesn't need to know, because the server is going to look at it and decide what to do with it. Okay, so the only person that needs to know is the server. The only thing that the routers need to know is where is it going, kind of thing. Okay, so generally everything is going to be in the envelope except for the IP address, more or less. Okay, so do I know that I'm getting an HTML file back? I don't. Okay, so I don't expect you to know the answers. I'm not asking the questions like you know the answers. I'm hypothetically asking them. Okay, so it doesn't need to know. Does it need to know that it's index.html, the name? Okay, that's stuff that will go inside the envelope. Okay, now what happens on the second request? Do I know that this user did one thing with Wikipedia and now they're doing something else with upload.wikipedia? So I do know that they visited the other website, okay? So I can see a packet, it's encrypted, I don't know what it says, but I can see something go to Wikipedia and come back, and then right away they go over to upload. I don't know what's inside, and then something comes back, okay? So that is something that I'm able to see as an adversary, okay? So I basically know what the users, who they're talking to, right? I don't know what they're talking about, more or less. Okay, so what we can do is you can break down the website. And so when I go and I load that particular website, I can actually do it for fun. Why not? Okay, so I load this website, wikipedia.org. You can see my browser is telling me, first it loaded the HTML file. The HTML file said, okay, go load this image, go load this, load this script, load this image, here's some other images to load. And so you can see all of this stuff like sort of coming down, okay? And it's all getting weaved in. Now, one thing you should be impressed by is look at all the stuff that came down. Okay, there's lots of like little files and different requests and things that were made. Okay, so it's not just like one thing came down. To make this website, there's probably, just eyeballing it, I don't know if it says 116 different things that came down. Okay, to make this exact website. Okay. Then let's think about, okay, what does the adversary see in the middle if this happened over a secure tunnel? Okay. So the first thing is there's the fact that, say it has a file name kit shorts Adidas short on black.png. Does the adversary know the name of that thing? So the answer is no. Okay, so the adversary doesn't know that. Does the adversary know that something went over HTTPS as opposed to not going over HTTPS? So the answer is yes. The adversary can see that. Okay. Do they know the domain name that I'm going to? Well, they know the IP address. Okay, you have to route it to the right thing. I can go to DNS and say, here's an IP address. What's the domain that's for that? And I can get the domain. Okay, so I can reverse DNS. So I do know the domain that's going by. Do I know that a file is a JavaScript file, a CSS file, a PNG file? I don't know that. Okay. What about the size of the file that's going by? So the answer is here. Okay, so the answer is yes. Why do I know the size of the file that's going by? Okay, but it's encrypted.
You know the size after the encryption.
Okay, so if I know the size after the encryption, does that tell me anything about the size before encryption? Okay, I have something that's 300 bytes. I encrypt it. Now I have a ciphertext. Is the ciphertext 300 bytes too?
Almost same.
Okay, so some people say yes, some people say no, some people say almost the same. Anyone that actually knows the answer can justify why? What?
Like if you are hashing, it will be fixed. Like,
Okay, so if I hash it, that's true. It will always come out the same, but then I can't go backwards. So I can't get a hash and recover it. Okay, can it be smaller? Okay, so the answer is no. Okay, if it's smaller, unless if you do some compression or something like that, but let's assume it can't be compressed, okay? If it's smaller, you're losing information. So if I send you something and make it smaller and send it to you, you can't unmake it small, okay? Compression will allow you to do it, but let's assume it's already compressed or whatever. Or there's some types of data that can't be compressed, like random data, okay? So if you want to recover every single bit that I sent, it's got to be at least the same size, okay? Now, could it be bigger? It could, okay? Is it the case that it will always be the same size? So if I send you a bunch of pictures and some of them are 3.4K, some of them are 1.23, some of them are 26, would they all show up being the same size? Okay, no. Why? Well, first off, yeah, I wouldn't know what size to send, right? Because I don't know what the biggest, I'd have to make it at least as big as the biggest thing, okay? All right, so the answer is that encryption basically is length preserving, okay? So your ciphertext is going to be more or less the same length as your plain text, okay? If you use something called a block cipher, it will round it up to the nearest 128 bits or 256 bits, okay? If you use something called a stream cipher, it will round it up to the nearest byte, okay? But when you're talking about things that are kilobytes and kilobytes long, those small, like, those are just rounding errors, okay? So more or less the size of the packet once it's encrypted is the same as when it's before it's encrypted, okay? So the adversary can infer the size of the thing being sent just by looking at how long the ciphertext is, okay? They don't know what it is. They don't know what the name of the file is. They don't know what type of file it is. They don't know anything. They just know this server sent it, and this is the size of it, okay? Now, it turns out that that length thing is actually pretty important, okay? So let's say I'm in the middle, and I see the user goes to Wikipedia. I know they're going to Wikipedia, okay? I don't know what article they're looking at. We agree, right? I don't know if they're reading the article about CF Montreal or they're reading the article about Montreal or Concordia. I don't know that from HTTPS, right? That would be in the file name here, and we said all the file names here are protected, okay? So I don't know that, okay? But I see they load some article, then they load exactly 115 resources, okay? And of the 115 resources they load, one of them is 17 KB, another one's 20 KB, another one's 3.4 KB, another one's 14.21 KB, one's 1.34 KB. If I go to Concordia's Wikipedia, is it going to have the exact same number of images as the Montreal Impacts website? Are they going to be exactly the same size? Okay, so I can look at actually just the number of resources that are loaded, the relative sizes of all of them, and think of that as kind of like a fingerprint. Okay, it kind of shows me, you know, you can sort of visualize what the fingerprint looks like by looking at like a picture, like, let's see, well, sort of like this, okay? So like every website will look slightly different in terms of when the packets arrived and how big they were and how many of them were and things like that, okay? And fingerprints, once you have hundreds of resources on your website and every website is different, like when I say a website, I mean like say every article within Wikipedia, most articles are going to have a unique fingerprint, okay? So I'm going to be able to guess. Now I might not be 100% accurate, okay? But I can get a good guess at which article you're looking at, okay? It would require me to first go to Wikipedia, download every article, and build what the fingerprint looks like. So I'll be like, this is what the fingerprint looks like for someone accessing Concordia. It has this many images in this size, and this is what the other article looks like. So I build up all these fingerprints. And there's complexities like, let's say I cache some of the images because I looked at a Wikipedia article. So then when I go to the second one, I already have the image, so I don't go out and ask the server so the adversary doesn't see it, or things like that, okay? But in security, we always think about the worst case. What's the worst case that could happen? So the worst case is that you're going to Wikipedia for the very first time, you have nothing cached, right? Does it protect you in the worst case? And so the answer is it doesn't. HTTPS does not protect you against fingerprinting, okay? So if an adversary can go and fingerprint a bunch of websites, they can get a pretty good sense of things that you're looking at. Okay, so even when it works exactly correct, there's no attacks. They know you're going to Wikipedia. They know you're looking at a page with, for example, exactly 87 resources. They know the size, more or less, like subject to rounding errors and encryption, but they know the size of every single resource. They also know the order. So usually you read the HTML from top to bottom. So the images that are kind of at the top, you're going to ask for first as you're still reading the rest of it, and then you're going to start asking for them as well. So they also tend to come in the same order. There's race conditions and things like that, so things may be slightly out of order. But again, if you just throw a machine learning algorithm or something like that at it and say, this is the general pattern, right, it does a pretty good job of picking out the right website.
It's kind of a dictionary, right? Instead of making a dictionary, we are making a fingerprint here.
Exactly, yeah. So the adversary first builds the fingerprint of the website. Then they do the best match. They say, I don't have that exact fingerprint, but it's way closer to this article than these other articles, so I'm going to guess this article. Yeah. So academics did this. So this was one example. So they went to a bunch of different banks, healthcare, streaming websites, and they did this attack, and they reported a 90% accuracy. Okay, so it's not perfect, it's not 100%, but it's very, very high. Okay, and this paper is quite old, and with like developments in machine learning and things like that, I'm sure you could crank it up past 90% at this point. All right, so what does this mean? Does this mean that when I go to Gmail and I read the first email in my inbox, that the adversary can fingerprint it and know what that email is? Why not? What's different about that than this?
It's private.
So I want it to be private.
The adversary cannot fingerprint something he does not have access to.
Okay. So in order to do a fingerprinting attack, you first have to get the real fingerprint of the thing. Okay? So this attack only works on websites that are sort of publicly available. Okay? So the adversary first goes to Wikipedia, they build the fingerprint, then when you go to Wikipedia, you see the same thing, then they can match the fingerprints. Okay? The adversary can open a Gmail account, they can fingerprint their own Gmail account, but my Gmail account when I log in looks completely different. Okay? So their fingerprints aren't matching what's in my actual account. Okay? So you can sort of distinguish the web between the public web, websites that if all of us go to the same website, we see the same thing, and the private web, meaning websites where we all go to the same, like we all go to mail.google.com, but we all see different things because it's personalized to us, because we logged in. Okay, it's like a login service. Okay, so fingerprinting, the good news is, the bad news is it works really, really well. The good news is it does only work on kind of public websites, or it does only work on public websites, okay? So that's still a pretty big threat model, but a lot of the things you really care about, like your social media or your email or your banking information, all that kind of stuff, this attack won't work on, okay? It does say banking, but the banking here was not like looking at your accounts. It was like, I'm reading about this kind of mortgage as opposed to this kind of mortgage, as opposed to this kind of credit card, like just the websites themselves. Okay, so fingerprint only works on public websites because the adversary needs to train on the public websites before they can do this matching attack. Still, it's a pretty bad attack.
So what if like the private website is like Concordia? The landing page is the same. Like if I log into my student account, everyone has the same
Yep. So in that case, the question is, was the adversary, like I could know that you're on your student account, but I don't know what your student ID would be because it will be different across the room kind of thing. You know what I mean? So it's like I could still track, like I could know that you're looking at your Gmail inbox, but I don't know the actual contents kind of thing. Yeah. Okay. Now, another question that I posed earlier. So we go to Wikipedia and we start downloading some images. And you saw, because the web is become very strict about these kinds of things, but you saw that when I download all of these resources, you can see there's a lock beside all of them. Okay. Now, Wikipedia mainly loads just from Wikipedia itself. Okay. It's sort of like a self-contained website. So they put all their infrastructure on it. But we said when I pull in a picture, I can pull it in from anywhere on the web. And what if the image hosting that I'm using and pulling in from doesn't have HTTPS? Am I allowed to pull it in over HTTP and put it in my HTTPS website? Okay. Am I allowed to do it? Is the browser happy about that? What does the browser do when it tries to decide whether to show me the lock or not? Would you show the lock if there's a website where some of the stuff on the website came over HTTPS, but other stuff on the website only came over HTTP? Okay. So yes, no, mostly. Okay. So let's see what happens. So what the browsers do is they actually start by dividing all the things that might get loaded into what they call passive resources and active resources. So passive resource is just something you look at, more or less. Okay, so it could be something like an image, an audio file, a video file, or an object file. And active content is content that runs, that executes code. Okay, so scripting would be the big one. So JavaScript is active content, PHP, any kind of scripting like that. And then there's some other stuff. So I won't go through all of them. XML, HTTP requests will become relevant later. That's requests that are made from JavaScript. So JavaScript itself, once you get JavaScript running, it can then tell your browser to go load a bunch of other resources as well through JavaScript. But those requests look different. It doesn't actually go over HTTP. It goes through a different protocol. Or it doesn't use standard GET requests. That may be a better way of putting it. Okay. All right. So different browsers will do it different ways. This is one of the browsers. I forget which one. And this is sort of generally true. So this is for Firefox. I see it now. What they decided is we will allow what's called mixed content. So mixed content means content that's over HTTP and over HTTPS. Okay. But what we're going to do is we're going to look and we're going to see whether the resources are active resources or they're passive resources. Okay? If they're passive resources like images, we don't really care that much. At worst, the adversary could substitute in the wrong image. Right? So you download the website, there's supposed to be a picture of Wikipedia of CF Montreal, and they put in Toronto FC's logo instead. Okay? So the adversary can mess around with websites. But that's considered not like a big threat, okay? A bigger threat would be if they could put JavaScript in, because once they put JavaScript in, JavaScript could actually rewrite the contents of the whole website. They could change everything, okay? And it could go fetch whatever else it wanted to. It could log your keystrokes as you were typing it into the website. It could pop up a login button and grab your password and send it off to the server. You know, it basically is executing anything, okay? So if JavaScript comes over HTTP, the adversaries in the middle, they can substitute their own JavaScript in instead, and it's going to run in your browser. Okay, so that's really bad. All right, so this is how they do it. Let me just go through, but you can see they have kind of like 3 different kinds of padlocks. So they show you the real padlock when basically when all the active resources came over HTTPS. If there's some active content mixed in, then they'll show you a lock with a line drawn through it. And okay. So let me rephrase this. If everything you get is over HTTPS, more or less, they'll show you a normal lock. If there's some images or passive resources that are mixed in the website, they'll show you a lock with this little like triangle with an exclamation mark. It's kind of like a warning. So it looks mostly like a lock, but there's something kind of funny about it. It just means there were passive resources. And then if active resources come, then it's going to put an X through it saying basically you shouldn't trust it. Now, in the extreme example, if the active resource is scripting, like JavaScript, now the policy in browsers is to block it. Okay? So it won't display the lock and warn you. It will actually just not accept that JavaScript. Okay? And then it will make a decision about whether to show you the lock or not based on what's remaining. Okay? So it will just block that, and then it will make a decision about the rest. Okay? And if blocking that JavaScript breaks the website doesn't work because it needs some JavaScript and you're not getting it, then too bad. Okay? So that's the sort of extreme measures that are taken now. Okay? So we can actually do this in Safari. So there's a website if you want to play around with this and see what different errors look like called badssl.com. And it has a whole bunch of like things that can go wrong, but you can see it. So okay, so this one loads a script, and it loads a script over HTTP, not HTTPS. But because I'm using Safari, Safari just blocks it. So Safari is no longer concerned about it because it blocked it. And I forget, it doesn't even show up in the resources because it was blocked, but it does trigger an error message somewhere. So here, the page at this was not allowed to run insecure content from nonsecure.js. Okay, so it just blocked that script, so it doesn't load it. But the rest of the stuff looks fine. I mean, it's just this document HTML file and then a style file that comes down with it. So that's fine. And then they have another one called Vary. And this one, you can see this is one of those weird examples where there's no lock. But if you click on it, it does say I loaded it over HTTPS. Okay, so this is one of those corner cases where I asked for it over HTTPS, so the browser remembers it, but it decides not to show me the lock because this website is so broken in terms of what it does. And so this has it loads insecure images, but it was allowed to display it. So it says, hey, this image came down. I'm displaying it anyways. There's a form. And the form is also insecure. And so if I try to type something in, I'll show you in a sec, you'll see what happens. And then there's also a JavaScript file that came down that is being blocked. And if I try to submit something to a website, like say there's a password field, I put my password in. If I'm on the website and it came over a secure tunnel, I expect the password to go over a secure tunnel, okay? But in this case, the website is wired to send it over a not secure tunnel. So what my browser does is it actually just warns me. So you've probably seen this warning before. You're going to send it in a way that's not secure. Are you sure you want to send it? And then you can decide whether to send it or not. Okay, so you get these warnings, and then it makes a decision about whether to display the lock or not. Okay, another attack strategy that we can do is, let's say that we're just observing from outside the tunnel. We can't decrypt it, okay? What we could do is just store it because encryption algorithms break, okay? It might take 10 years, it might take 30 years, we might need a quantum computer, okay? But eventually we might be able to break the encryption. And so if we just store everything today, then there might be like some future time where we could break it. There might be some weakness in the algorithm that we don't know today, okay? Now, who's the adversary that would be doing this kind of attack? right? It's not like me or you, right? It's going to be like a nation state, for example, like the NSA, which is the secret security agency in the United States, who happened to build a very big data center, right, out in the middle of Nevada in Utah. And, you can see it from satellite. No one knows what it's for, but there's a lot of storage capacity in that building just from looking at it from satellite images and things like that. Okay, so the theory is that they're just storing everything. There are certain conversations that might happen online that could be relevant in 30 years from now to a nation state between people. Okay, so anyways. Now, there is this concept of perfect forward secrecy, which is a crypto property. You'll learn about it in 6110, hopefully. And so it basically says that if I break into your server and steal every key that you have, I can impersonate you going forward. And because I can impersonate you going forward, I can read all the conversations people try to have with you. But every past conversation you had, I can't break with those keys. There's other ways maybe of breaking them, but those keys don't let me break them. Okay? Not all of HTTPS has this property. So if we went back to the early diagram of SSL 2.0, 3.0, TLS 1.0, 1.1, there was a certain point where that was introduced, and then it was an option. So you could choose, basically the server and client kind of negotiate what they want to do, and they might choose to use one of these algorithms or not. The latest version of TLS only has these algorithms. Okay, so you'll never negotiate, or I shouldn't say it, if you hit an old server that doesn't support the nearest version, you could still negotiate an algorithm that doesn't. But assuming the server's up to date and you're up to date, then you'll always do something with this perfect forward secrecy. Okay, so what we can do is we can put everything we talked about in this sort of sub part of the tree. So the sub part of the tree was we're going to break HTTPS by looking at what we could see from the outside. So first off, we can just learn all the content that doesn't go over HTTPS. Okay, so the domain that's being visited will be in the header, or the IP address technically. When the person hits DNS, we'll also know that information. And any content that gets mixed in that doesn't go over HTTPS we'll also be able to see. Okay, and change if we want to. Now, changing is important because if I can modify JavaScript, then I could actually learn what else is on the website. Because JavaScript it gets loaded into the browser, and the browser gives it access to all the other resources that are loaded for the website. It has read and write access, plus it has the capability of opening connections to arbitrary points. Okay, so if I can get my JavaScript mixed into your website, then I can read all the other stuff that's being shown to you. I can change it all, and I can phone home with whatever I see. But the good news is that now browsers will block JavaScript that comes down that's not over HTTPS. Okay, it won't even warn the user. It won't put a funny lock icon. It will just straight up block it. The next thing I can do is fingerprinting. So I still, even though I don't know the content of what's being sent back and forth, I know how many packets, what's the order of them, what the relative sizes are, and so this lets me fingerprint. But fingerprinting attacks only work on public websites. So they're not going to work on every website, but it will work on public websites. And then if I'm some sort of nation state, I might just store everything and hope I can break it later. Okay, questions about this portion of the tree? Okay. Okay, so we had three kind of high-level strategies. So the first was, assuming everything works right, what can we learn just by watching what goes on? Okay, so that's everything that we just talked about. The next thing we'll try and do is break into the tunnel. And then we'll spend a lot more time on the third one, which is we're going to try and get the tunnel to end at us instead of where it's supposed to be going. Okay, so to break into the tunnel, what we want to do is we want to break the cryptography that's in used. And the cryptography that's used is quite complicated. Okay, so you would have to more or less take 6110 from start to finish, and maybe on the last day of 6110, you would know all the pieces to put together that is used in a protocol like this. So when I teach 6110, I do show you this protocol, but it's literally the last lecture because it uses every single piece of the lecture in order to build the whole protocol, okay? Not everyone here has taken 6110, right? And so I'm going to assume that you haven't. And so there's no way I can actually like really show you these attacks and how they work, okay? So what I'm going to do instead is I'm going to try and give you the flavor of how they work. And then if you have taken 6110, it might make more sense to you. And if you want to do a project in this area, you can do a project in this area, and then this will sort of help you out by pointing out places that you can look, okay? But I'm just going to give you this section of the tree will be a little light on detail. I'll just try and give you the high level. Okay. Now, the way cryptography works is we have these keys. And a key isn't like a physical key. It's like a password. It's just longer and more random. Okay? And at the end of the day, once the tunnel's in place, your browser and the website that you're visiting have a key that's the same number. Okay? So just think of it as a big, long number. You have a copy of it. The website has a copy of it. When you send data, you use it to encrypt. When they receive data, they use it to decrypt. Okay? When you send data, you do something called a MAC, which is kind of like signing it. And then when they receive it, they use their key to check whether it changed or not. Okay? So those are the two properties, confidentiality and integrity, that you want. The server authentication is already done at this point. So at this point in the story, we have a tunnel. How do we know the tunnel ends where it ends? Well, that we'll explore when we look at the third category. Okay, so there's some crypto into this, and there's a different kind of crypto that tries to give you this. Okay, but at this point we just care about integrity and confidentiality, and for our attack tree, because we're trying to read information, we actually just care about confidentiality. Okay, so the story here is really simple. If you can get that key either from the browser or from the server, then you can break into the tunnel. If you cannot get the key, you cannot break into the tunnel. Okay? There's not enough computers in the world that would let you break into the tunnel without the key. Okay? So all of these attacks are going to be, some of them will be about getting the key, and then some of them will be like, what can you do if you don't have the key? Can you really do nothing? And so it turns out you can do some things if you don't have the key. Okay, so either you're going to try and steal the key, or you're going to see what you can do without the key. Okay, so how do we steal the key? Okay, so one way of stealing the key is called side channel analysis. And so what side channel analysis means is you sort of do something that the protocol doesn't account for. And so the best way to describe it is with what's called a timing attack. So what I'll do is I'll send a packet to you, and you're going to use the key to decrypt it. Okay? And what I'm going to do, and then say when you're done decrypting it, you're going to send me a message back. And I'm going to measure how much time it takes you to decrypt. Okay? And there's going to be slight variations, there could be slight variations in how long it takes you to decrypt, depending on what your key is. So this is not true at all mathematically, but just to give you the flavor. Imagine your key is like a whole bunch of ones, like 1, 1, 1, 1, 1. Okay? It might take you longer somehow to decrypt with that key than if you had a key with a lot of zeros, like 0, 0, 0, 0, 1, 0, 0, 0, 0. Okay? Okay? That's not exactly the mathematical truth, but it gives you kind of the picture. Okay? So depending on the exact value of the key, the amount of time it takes to decrypt is slightly different. Okay? And if I send you enough packets and I have a good enough clock, I might be able to start to infer what your key is by seeing those patterns over time. Okay? So it turns out that this was actually somewhat practical. It's hard to do over the internet, but if I'm like, say, on Ethernet with your computer, so I'm like very close to it in the network and I can measure things more carefully, I can do some stuff on older algorithms. So there's this algorithm called RSA, and it had this weird padding scheme because you had to make the messages a certain size so that you can encrypt them, but sometimes they spilt over, so you could measure when it spilt over and when it didn't, and it would tell you a bit about what the key was. So anyway, so this type of thing works. It tends to work in the lab environments. In the wild, it usually you can't get like that sensitive time information. Anyways, today what crypto people do and what every modern implementation of SSL TLS will do is they'll make sure every operation takes the exact same amount of time regardless of what the key bits are. Okay, so even if there's a shortcut where, oh, there's a bunch of bits that are 0, I can skip a couple steps. The algorithm will purposely do those steps even though they don't have to, just to make sure that it takes the same amount of time regardless. Okay, so all libraries have been gone through by developers and auditors and people looking for these kinds of attacks, and they're hardened against those attacks, meaning people put a lot of brain power into doing it. Does that mean they're completely invulnerable to the attack? Not necessarily, okay? Maybe there's something that they didn't think of, okay? But they are hardened. So people know about these attacks. They spend a lot of time doing it, okay? So it tends to not work. Now, the reason I like to bring this up in the security course is forget about HTTPS for a second, okay? Just as a general class of attacking anything that you might want to attack, this idea of side channel is very important. Okay, it works on all sorts of different kinds of things. Okay, so the amount of time that something takes, that's one form of side channel analysis, but there's other things. So for example, you can look at power consumption. So if you have a very sensitive voltmeter or something and you plug, so there was ATMs used to be that you could plug them into a voltmeter, plug the voltmeter into the wall. And then when a person pressed their pin in, right, when they press 3, it like kind of draws a little bit of voltage, right? But if they press the 1 key, it's slightly different because the resistance is different or something. I forget my electrical engineering, but there's something different about it. It is measurable if you have a sensitive voltmeter, okay? So it's sort of a timing attack. You're watching them press their pin in, so you know when they're doing it. Then you go to the chart of the volts, and you can kind of read out what their pin is, okay? Similar thing, this was actually done with a voting machine. So there were these voting machines. Same idea, when you press to vote for a candidate, it was a button. So candidate 1 had a button, candidate 2 had a button. In this case, they were measuring the kind of the sort of noise that the machine makes on the radio spectrum. Okay, so electronics are always like making like noise, and you need a sensitive antenna. But in this case, they could actually stand outside of the building just with a radio, and they could measure the changes in the radio frequency every time someone pressed a button, and they could figure out what buttons were being pressed, therefore what people were voting for. There's a guy, I saw a talk when I was a student from Adi Shamir, who's the S in the RSA algorithm, which is one of the first crypto algorithms. So he came and he's like, you know, I had this computer, it was sitting on my desk, and it was really loud. You know, now you don't hear it so much with laptops, but like back in the 90s or 2000s, like computers were loud. Like they were always like crackling and making all kinds of like weird noises, right? And he's like, I couldn't figure out what that is. So I had this idea. So I decided to like encrypt things with RSA, and I would just like record the noise. And then I would try to figure out if you could figure out what the key is based on the noise. And it turns out you could. You could basically read the key out because the noise it would make is slightly different if the bits were 0 or 1. Again, that's obscuring the details. It has more to do with the math that's involved, but yeah. On cell phones, so cell phones have very sensitive gyroscopes, right? If you want to rotate your phone, it needs to know that. But also, like, there's augmented reality where you like sort of scan and then it puts an object, and so now they know it. So when you're typing on your phone, you're actually like slightly like rocking your phone, right? And when your finger hits the phone, it vibrates a bit. Okay, and if I hit my phone way over here, it vibrates a little different than if I hit it in the middle. Okay, so if you have access to the data from the gyroscope that's in the phone, and you know a person's about to put their password in, right? You can actually read the keys off that they're pressing based on where they're pressing on the phone, based on how much it's vibrating. Again, you have to train first, so you have to do a bunch of training first, and then you get it, but that type of thing. And then there's a bunch of work on like reflections and things. So like, say someone in the building across has like a video camera with a powerful lens, and so it's looking at my glasses, and my laptop screen is being reflected in my glasses, and they can see it from across the building. Could they reconstruct what's on my screen? And the answer is yes. In a lot of reasonable circumstances, you can do that kind of thing, okay? So anyway, these are all examples of what we call side channel, because the protocols don't account for it. It's not in the threat model of the protocol. You're attacking it from the side through some other mechanism.
Excuse me, Professor. What is CF?
This DRE?
No, power call.
Oh, CF. Sorry, CF means like, for example, kind of. Yeah, sorry, it's just like EG or IE. It just means compare to. It's Latin for compare to, mostly. Yeah. Okay, let me tell you another story. So this is something called Heartbleed. So this was a big vulnerability. I forget the date of it, but it was like a while ago, like 10 years probably. And so, okay, so this is how the web works. You have a bunch of servers that are on the web, and Heartbleed's a software implementation error, okay? And it only exists in certain kinds of software, not in all kinds of software, okay? So in order to exploit this heartbeat vulnerability, you need servers to run a very specific kind of architecture, okay? So the operating system they had to be running is called Apache, okay? Apache is like a free Linux style like thing for servers. Then they have an implementation of SSL TLS. And so the implementation they would have to be using is OpenSSL. And then OpenSSL would have to have this heartbeat protocol turned on, which we'll talk about in a minute, okay? Now, even though this is pretty specific, Apache is very, very popular. And if you just tell Apache, hey, I want SSL support, you press a button and OpenSSL is the default that it gives you, okay? And at the time, if you put OpenSSL by default, unless if you did something special, Heartbeat would be turned on, okay? So basically, everyone that was running Apache that wanted to do TLS would have this exact configuration. And so it was estimated that about 40 to 60% of the web had this, okay? The other percentage would be running Windows, Microsoft products, or something else. Apple has some, but they're sort of obscure. Okay, so the idea of the Heartbeat protocol was, actually no one really knows why it was there. It was in OpenSSL from the very beginning, and it was kind of like a debug thing. And the way it worked is you would, oh, I should note just for interest, the person who coded up OpenSSL initially, he just did it as a fun way to learn C. He's like, I just wanted to learn C, so I made a crypto library. And that's how I taught myself C. But then it became popular, and because it was open source, lots of people worked on it. And today it's still the standard implementation of a lot of crypto. Okay, so the Heartbeat protocol was more of a networking thing. It was meant to see whether a server was online and responsive. It was kind of like a fancy ping for the server. So what you would do is you would bounce a message on the server like A, B, C, D, E, F, G, and then it would repeat it back to you if it was on, it had OpenSSL configured correctly, it had this protocol turned on, then you would know, okay, this server is able to talk OpenSSL, okay? Then for whatever reason, they decided, what if you don't want to get the full message back? What if you're okay just having the first 3 characters or the first 5 characters instead of all of it, okay? So they had this extra parameter where you could say, okay, here's a string, echo it back to me, but you can just stop after 5, okay? So it would send A, B, C, D, E, or whatever, all right? And so that was the protocol, more or less. It's a vast simplification, but that's sort of what it was meant to do. You can kind of see it's sort of a liveness test for servers. You can make sure your messages are being routed correctly. You can make sure that anything that's in the middle that might be changing it, it's not being changed because you're getting back the same message that was sent and things like that. Or it's not an accident. You could just say, hey, are you there? And it says yes, but maybe it's saying yes to some other question, okay? So it's just a way of sort of knowing that it's answering you explicitly. Okay. Now, we can ask for, say, 1 character back. We can ask for 5 characters back. There's 1, 2, 3, 4, 5, 6, 7 characters. We can ask for all 7 characters back. What happens if I ask for 8 characters? I say, here's a 7-character string. Don't worry, you don't have to send all 7 back to me. Just send the first 8.
It returns the buffers pointer top of the one.
Okay. So hopefully it would say, sorry, you sent me something that's 7 characters. I can't return you 8 because 8 is bigger than 7. Okay? But if it's not coded correctly, okay, if it's coded in C, right, where data is written into memory and you have a pointer to memory, and normally when you read from memory, you just say, here's a pointer, here's how many bytes I want you to write, or read, sorry. Just start there and finish when you finish, right? There's no like type checking or things like that, type safety. And so a lot of C programs are vulnerable to this kind of thing, which is called a buffer. Well, there's different names for it. So buffer overflow is technically something slightly different. This is called a buffer underrun. But anyways, so basically that's what Heartbleed was. Okay, it was a vulnerability in the protocol where you could say A, B, C, D, E, F, G, echo back 1,000 characters. Okay, then what it would do is it would read the first characters back. Okay, in that memory location. Then it would keep going. What does it mean to keep going?
It reads next.
Keeps going in memory, right? So it's reading. So where's it going next?
Recent data like in the stack, like username, password, and like SSL keys because it's stored before I started computation.
Okay. So the memory is like the temporary memory, the RAM of the server. And so it's just going to read whatever's next to this wherever it's stored it's going to read what's next to it in RAM. Okay? And it's implemented as a stack, so the things that are next to it will be the things that were most recently recorded by the server for whatever reason. Okay? So the server is writing a bunch of stuff into RAM because it needs it. So it might write a password into RAM because it has to hash it and then check it against its password database. Okay? So all of that is like happening in RAM, so it's just lying there waiting. Okay? So what you get is you basically get a way to dump the contents of RAM on the server, and whatever's in RAM you get. Okay? Now you can't get all of it. There was a bound on this, but the bound is pretty big. It's 64 KB. Okay? So you can dump 64 KB of the most recent stuff that the server did. Then you can wait a while and hit it again and get the next 64 KB and keep repeating it. Okay, so what are the kinds of things that might be in RAM of a server that you might care about keeping private? So things like usernames and passwords, because you have to process the passwords. Cookies we'll talk about at the end of the course, but they're another kind of secret value that if you have it, it's more or less like having someone's password. There could just be data. So like, for example, someone uploaded their tax documents, and so it's a PDF and it's sitting in RAM. Okay, that could be in. Okay, now the one thing that people were concerned about is, could you get, I'm going to slightly backtrack what I said earlier. So I talked about keys. Okay, so I said a secure tunnel is you both have 2 keys. Okay, so that is true. Okay, and those keys are called session keys because it's just for one session between one browser and one server. And if 1,000 users are accessing a server at the same time, then the server has 1,000 session keys, one for each session. Okay, so those session keys are definitely in RAM. You can get those. Okay, but in order to get those session keys, the server also has one like super secret key. It's like a master key that it uses for all of its session keys. Okay, we'll meet it a little later when we talk about server authentication, but just know that it's there. Okay. And so the big open question was, could you use Heartbleed to get that long-term TLS key? Okay, and a lot of people theorized that the answer was no, and this is their reasoning. When you first turn on the server, that's the very first thing you load into RAM, okay, because you need it immediately. Okay, so it's the very first thing that goes into RAM. Then the server runs for days, months, years, and there's a bunch of other stuff happening. And so that key is so deep in RAM that if you can only pop the most 64 most recent stuff, you're never going to hit it. Okay? So that was the theory behind it. And there was a big company, I forget which one, they actually went on record saying, if anyone can get our long-term session key out of RAM using Heartbleed, we'll give you $1 million or something. I don't know what it was exactly, right? So then someone very clever, they came up with an attack. And what they did is they found another vulnerability where they could force a server to reboot. Okay? So they triggered one vulnerability. It forced the server to reboot. Then they hit it with Heartbleed as soon as it went online. Now the key is like in that 64 KB window, and then they were able to get the key. So they were able to extract it. Now Heartbleed is, it was like all over the news. Like this isn't just like some obscure thing that I'm telling you about. Like it was on CBC and things like that. There were all sorts of websites that were vulnerable. One website was the Canada Tax Agency, so the CRA. There was a kid who was just a student, and he read about this Heartbleed thing, and people made code for it. So like with Metasploit or whatever, you could just run it if you wanted. He wasn't thinking twice. He was just like, oh, I wonder if CRA is vulnerable. And so he did it. And then he saw a whole bunch of private tax information and stuff like that. And everything is logged, right? So it probably took them a year, but eventually they went through those logs. They saw that he had done it. And so they actually charged him criminally. And so there was this big trial, and he was just fooling around more or less. So anyways, let that be a warning to you, don't fool around, okay? Now, in the end, it wasn't so bad. He pled guilty, so there was a charge, but they understood that he wasn't malicious in his intent, and I forget what the punishment was, but he didn't go to jail or anything like that. But anyways. Okay, so that's Heartbleed. Now, another kind of general category of attack is called a downgrade attack. And so for clients and servers to do encryption, they both have to support encryption, obviously. And it turns out there's lots of different ways of doing encryption. There's lots of different versions of SSL, and different versions of SSL come with different ways of doing encryption. People come up with newer, faster algorithms. They're introduced. And so at the end of the day, you have 50 different options that you could choose across all the different versions of things, okay? So how does the server and client actually figure it out? The answer is they negotiate, okay? So basically the client says, here's everything I know. And the server says, it could say, here's everything I know, and then we'll pick it. But what actually the server does is just reads the list and says, okay, the thing that I know that's the best thing on your list, I'm going to use, and that's what we're going to use, okay? The problem is we don't have the tunnel yet because we're negotiating how we're going to set up the tunnel. So if we don't have a tunnel and we're trying to set the tunnel up, then the adversary can be in the middle and they can see how we're trying to set up the tunnel, and there's no integrity either. So I can say, hey, I want to do AES 256 GCM, and the adversary can say, hey, I want to do DES 56, which is a super weak cipher that I could crack on my laptop, but was supported at one time in TLS, okay? The server will say, oh, this guy only supports DES. That's weird, but I do support it. I have my, I'll dust off my, library from the 90s, and I'll support it. And then we'll start talking with this encrypted channel, and then the adversary can just read it, okay? So this type of, adversary that jumps in the middle of the negotiation stage and tries to get you to use old stuff that's broken is called a downgrade attack. Okay, so they're trying to downgrade you. So they might try to downgrade your version of TLS, maybe down to SSL 2.0, which was in the 90s. It might try to downgrade the encryption that you choose. So this is called the cipher suite. And it might actually downgrade you to no encryption at all. So that was an option at one time as well, that was supported. And clients and servers maintain a big, long list of these things because you never know when you're going to be a server that hasn't been patched in a while, okay? Now, TLS has some protections built into this, okay? So the protections sometimes came after there's attacks. So there was attacks and then they changed how it works. And then the newer versions have very strong protections against this, okay? So if you're using TLS 1.3, you basically can't downgrade. And it's complicated to explain why, but it sort of more or less works. But software implementations don't always implement things exactly by the spec, or sometimes the spec is kind of ambiguous or vague about things, and so software just has to decide how to implement it. And so the actual software implementation might leave some vulnerabilities to downgrading in place, even though they're not part of the protocol itself. Okay? So there are some attacks along those lines. We'll talk about them, we'll go through them, but we're not going to do it today. We'll do it next class because we're completely out of time. So any quick questions? All right, so I'll see you all next week.